For over 50 years, the idea of a fully reusable heavy-lift rocket was treated as a fantasy by the aerospace industry. The physics appeared insurmountable because the fuel needed to land a vehicle the size of a skyscraper would leave no room for cargo. Every major player, from legacy giants to government agencies, believed that the extreme heat of re-entry would inevitably destroy the precision hardware required for a safe second flight. NASA's Space Launch System attempted to bridge this gap, but it remained a compromise that cost billions per launch and required months of maintenance. Industry experts concluded that throwing the rocket away was simply the price of doing business in orbit. Then SpaceX unveiled Starship and transformed the logic of spaceflight forever. This is the story of how they turned a mechanical impossibility into a routine reality. The challenge of reaching space is governed by the rocket equation, a harsh set of mathematical rules that dictate how much fuel is required to lift a specific amount of weight. Historically, this meant that about 90% of a rocket's mass had to be fuel, leaving very little room for the actual structure of the ship. To maximize efficiency, engineers designed rockets in stages that would fall away and burn up in the atmosphere once their fuel was spent. This disposable approach was the only way to ensure enough speed was reached to stay in orbit. The world accepted this waste as a necessary cost. When NASA developed the space shuttle, the goal was to create a reusable system, but the design was flawed. The shuttle required a massive orange fuel tank that was destroyed during every mission, and the side boosters were dropped into the ocean where salt water corroded their parts. The cost of fixing the shuttle after it landed became so high that it never lived up to the promise of cheap space travel. For decades, companies like United Launch Alliance and Boeing maintained that the only way to be reliable was to build a new rocket for every single flight. This industry consensus was rooted in the extreme technical constraints of atmospheric re-entry. When a vehicle returns from space, it travels at speeds exceeding 17,000 miles per hour. As it hits the thick air of the lower atmosphere, the friction creates temperatures reaching over 3,000 degrees Fahrenheit. Most aerospace materials, like aluminum or carbon fiber, lose their structural integrity at these temperatures. Aluminum begins to soften and melt, while carbon fiber can become brittle or catch fire. To protect the vehicle, engineers had to use heavy, expensive heat shields. On the space shuttle, these were thousands of ceramic tiles that were glued on by hand. They were incredibly fragile and often fell off, requiring weeks of inspection and replacement. The expert view was that the weight of a heat shield strong enough to be used many times would make the rocket too heavy to carry any meaningful cargo. This was the wall that every engineering team hit for half a century. They believed the physics of heat and weight made a fully reusable ship a mathematical impossibility. Furthermore, the landing process itself presented a massive hurdle for large-scale vehicles. Landing a rocket vertically requires the engines to fire with incredible precision while the ship is falling backward toward the Earth. Most rocket engines are designed to be either on or off. They operate at a single high-power setting to fight gravity during takeoff. To land, an engine must be able to turn its power way down, a process called throttling, so it can hover and touch down gently. If the engine is too powerful, the rocket will simply fly back up into the air. If it is too weak, the rocket will slam into the ground. Legacy engines, such as the Russian-made RD-180, were powerful but lacked the fine control needed for a vertical landing. Additionally, the legs required to support a 230-foot tall booster are incredibly heavy. Every pound spent on landing gear is a pound that cannot be used for satellites or crew supplies. Engineers at major firms argued that the fuel and hardware needed to land would use up more resources than the rocket was worth. They saw reuse as a trap that would make spaceflight more expensive, not less. Here's how they actually did it. The breakthrough came when the engineering team moved away from traditional materials and chose to build Starship out of 300 series stainless steel. This was a radical departure from the carbon fiber and aluminum used by every other rocket company. Stainless steel material has a unique property. It gets stronger at the extremely cold temperatures of liquid oxygen and methane fuel. Just as importantly, it has a much higher melting point than aluminum. This allowed the engineers to simplify the heat shield. Instead of thousands of different tiles, they could use a more uniform system of hexagonal plates. The steel body of the ship could handle more heat, which meant the heat shield didn't have to be as thick or heavy. This saved thousands of pounds of weight. The second major innovation was the Raptor 3 engine. This engine uses a full-flow staged combustion cycle, which is the most efficient engine design ever created. It uses all the fuel and oxidizer to spin the pumps before they enter the main chamber, creating massive pressure. This design allows the Raptor to produce 1,680 tons of thrust, which is enough power to lift about 50,000 pickup trucks at once. The Raptor engine also solved the throttling problem. Unlike older engines that were like an on-off switch, the Raptor can change its power level from 40% to 100% with extreme precision. This gives the flight computers the ability to adjust the thrust in real time to keep the rocket balanced as it descends. To solve the problem of heavy landing legs, the team invented a ground-based solution called Mechazilla. This is a massive launch tower equipped with two giant steel arms. Instead of the rocket carrying its own legs to the moon and back, the tower uses its arms to catch the booster out of the air as it returns to the launch site. This moved the weight of the landing gear from the rocket to the ground. By removing the legs, the ship can carry 100 tons of cargo to orbit, which is more than any other rocket in history. This combination of material science, advanced engine cycles, and robotic infrastructure broke the technical cycle that had kept spaceflight expensive for generations. The transformation was further enabled by the use of grid fins and supersonic retropropulsion. Grid fins are small, waffle-shaped paddles at the top of the rocket that steer it through the air. They work like the wings on a plane, but are much more effective at the high speeds a rocket reaches during its fall. When the booster hits the thicker air, these fins move independently to guide the 230-foot tall tube back toward the launch tower. At the same time, the engines fire while the rocket is still moving faster than the speed of sound. This creates a cushion of gas that acts as a shield, pushing the high heat air away from the bottom of the rocket. This technique, which many experts said would be too unstable to work, is what allows the engines to survive the return trip. By mastering these specific systems, the team proved that a large-scale vehicle could be controlled with the precision of a much smaller craft. This technical victory has translated into a massive competitive lead. The numbers show a level of dominance that the industry has never seen before. One launch of the NASA Space Launch System costs your tax dollars $4.1 billion according to government reports. For that same amount of money, SpaceX could launch Starship over 400 times. This is the difference between buying a high-end luxury car and buying a single cheeseburger. The cost of sending 1 ton of cargo to space was previously about $90 million. With this new reusable system, that cost drops to about $100,000. This change in economics is why SpaceX now handles the vast majority of the world's satellite launches. In 2023 alone, they launched more mass into orbit than the rest of the world combined. While other companies take years to build a single rocket, the Starship factory is designed to produce one ship every week. This high speed of production allows the team to test new ideas and fix problems in real time. If a ship fails during a test, they have another one ready to fly in days, not years. The competitive scoreboard is equally lopsided when looking at other major players. Boeing's Starliner program has struggled with significant failures, including software errors during its 2019 orbital test, and further delays that have kept it from being a reliable transport for astronauts. The contract for Starliner cost billions, yet it has failed to reach the flight frequency of the Crew Dragon. wagon. While legacy firms are stuck in a cycle of delays and cost overruns, SpaceX has completed over 200 successful landings of their Falcon 9 and Starship vehicles. This success rate has convinced the market that reuse is not just possible, but essential for survival. Competitors like United Launch Alliance are now scrambling to find ways to recover their engines because they cannot compete with the low prices of a reusable fleet. The strategic intelligence of the reusable model has protected SpaceX's resources and allowed them to reinvest in even larger breakthroughs. This dominance is not just about cost, it is about the frequency of flight. The ability to fly the same hardware twice a week, every week, has turned space into a routine environment. In the past, a rocket launch was a rare event that required months of preparation. Now it is becoming as common as a cargo ship leaving a port. This launch frequency is what allows for the creation of massive satellite networks like Starlink. Without a reusable rocket, the cost of launching thousands of satellites would be so high that no company could afford it. Because the Falcon 9 can land and fly again in as little as 21 days, the cost is low enough to make global high-speed internet a reality. This is a clear example of pattern recognition in action. The team saw that the only way to build a massive business in space was to break the link between the number of flights and the number of rockets built. By making the rocket a service rather than a product, they changed the entire game. The human decisions behind these engineering wins also tell a story of strategic mastery. While government agencies often operate on a system of consensus and slow approval, the development of Starship was driven by a philosophy of fast failure. The team would build a prototype, fly it until it broke, and then use the data to build a better version. This is how they solved the problem of the landing flip maneuver. Early versions of the ship crashed because the fuel would slosh around in the tanks, causing the engines to cut out. Instead of spending 5 years in a lab studying the problem, they flew 5 ships in a row. They tried different tank shapes and different plumbing until they found the one that worked. This hardware-rich approach allowed them to move faster than any government program in history. It demonstrated a level of technical mastery that comes from doing the work rather than just talking about it. The consequences of this breakthrough are just beginning to be felt across the world. With a 100-ton cargo capacity and a low price tag, we are no longer limited by what we can carry. In the past, every piece of a space station had to be designed to be as light as possible, which made them incredibly expensive and fragile. Now we can send heavy shielding, large water tanks, and industrial machinery into orbit. This makes a permanent base on the moon a real possibility. We can send the heavy equipment needed to mine the moon for water and fuel. This also serves as a bridge to Mars. If you can land 100 tons on the moon, you can do the same on the red planet. The gap between science fiction and engineering reality has been closed by the power of the Raptor engine and the strength of stainless steel. Furthermore, this transformation has major implications for national security and global communication. The ability to launch on demand gives a significant advantage in maintaining orbital infrastructure. If a satellite is damaged, a replacement can be sent up within days. This level of responsiveness was previously thought to be impossible. The justice of this achievement is seen in the shift of the entire industry. For years, critics said that reuse was a waste of time and that SpaceX was taking too many risks. Now every major space agency in the world, including those in China and Europe, is trying to copy the Falcon 9 and Starship designs. They have realized that the old way of building disposable rockets is a dead end. The competitive scoreboard has been reset, and the rules of the game have been written by the team that was brave enough to try what everyone else said was impossible. The mastery of these systems also enables the dream of point-to-point travel on Earth. Because Starship can fly through the vacuum of space where there is no air resistance, it can travel from New York to Shanghai in about 30 minutes. This would turn a 16-hour flight into a short trip. While this is still in the testing phase, the physics are now proven. The same engines and heat shields that allow the ship to return from orbit can be used to facilitate high-speed travel across the globe. This would transform international business and travel in the same way that the jet engine did in the 1950s. The strategic intelligence of the design allows for multiple uses of the same technology, maximizing the return on every dollar spent. Looking forward, the development of orbital refueling will be the next major breakthrough. Starship is designed to be refilled in space, much like an airplane being refueled in mid-air. This allows the ship to take its full cargo load all the way to Mars. Without refueling, a rocket loses most of its power just getting off the Earth. By launching tanker versions of the ship, the fleet can create a gas station in orbit. This turns the Earth's orbit into a jumping-off point for the rest of the solar system. The competence hierarchy in aerospace has been reorganized around this ability to manage complex operations in space. The teams that can master refueling and long-term storage of fuel will be the ones that lead the next century of exploration. The impact on the environment is also a key part of the story. While throwing away a rocket leaves thousands of tons of metal at the bottom of the ocean, a reusable rocket keeps that material in use. The transition to liquid methane and liquid oxygen fuel is also a cleaner alternative to the solid rocket boosters used in the past. Solid boosters release harmful chemicals into the atmosphere that can stay there for years. Methane burns much cleaner and can even be produced on Earth or Mars using CO2 and water. This creates a sustainable loop for space travel that doesn't rely on depleting rare resources. The resource protection inherent in the design is a core part of why it will succeed in the long run. The story of Starship is ultimately a story about the power of engineering to change the world. It shows that the impossible is often just a problem that hasn't been solved yet. By questioning the basic assumptions of the industry and focusing on the physics of the problem, the team was able to achieve what the giants of aerospace could not. They didn't just build a better rocket, they built a better way to think about difficult problems. They proved that with enough determination and technical skill, the stars are within our reach. The pattern recognition that led to the choice of steel and the development of the tower catch has paid off in a way that has changed history. The competitive victories continue to mount as the fleet grows. Each new launch provides more data, making the system safer and more efficient. We are seeing a shift from experimental flights to a routine transportation service. The future projection for this technology is a world where space is no longer a destination for a few brave astronauts, but a workplace for thousands of people. This is the ultimate victory of the magician archetype, the transformation of a hostile and unreachable frontier into a place where humanity can thrive. The technical mastery of the Raptor engine and the strategic intelligence of the reusable fleet have made this possible. The shift from disposable to reusable rockets is the most significant event in aerospace since the moon landing. It proves that with the right technical approach, even the most difficult physical constraints can be overcome. We are no longer limited by the high cost of throwing away our transport. The justice of this success is found in the results. Those who said it could not be done are now watching as it happens every week. The information hunt continues as engineers look for ways to make the engines even more powerful and the ships even lighter. Every launch provides more data to refine the process. We are watching the birth of a new transportation system that will eventually take people to other worlds as easily as we fly across the ocean today. The mastery of the landing, the strength of the steel, and the power of the Raptor engine have combined to create a revolution. SpaceX didn't just land a rocket, they turned a miracle into infrastructure. Over 200 landings while Boeing's Starliner hasn't flown crew reliably and Blue Origin hasn't reached orbit. The impossible became infrastructure. Now Starship aims to do the same at 10x the scale, turning Mars from science fiction into an engineering problem.